Welcome to the lesson on similarity analysis across transport phenomena. This is part of the unit on mass transfer, which is being taken up as NPTEL MOOC on transport phenomena in materials. This analysis is mainly due to Osborne Reynolds, who in 1874 noticed a similarity between energy and momentum transfer. He presented his work in 1883 on frictional resistance to fluid flow in tubes, and then it paved the path to have a quantitative analogy between these two phenomena. Later on, this has been expanded by Chilton and Colburn in two separate papers where such an analogy is possible across all the three transport phenomena. Let us look at how this has come about. So consider the problem definition as follows. There is a fluid which is on the surface of a solid, and at the interface we look at the profile of the velocity, the temperature field and solute field. So we draw the velocity profile as here the velocity as a function of y, and we can also draw the thermal profile and the solute profile. So due to no slip condition, the velocity profile would have 0 at the interface between the fluid and the wall. However, that need not be the case for temperature or solute, and therefore you have Ts and Cs, which are the temperature and the solute concentration at the wall. So what we want to propose is that under certain flow regimes it could happen that these profiles are similar in appearance. When we say similar in appearance, we cannot actually take the absolute profiles and compare them. The reason being that along the distance the temperature profile would actually change, because as the fluid is gaining heat from the wall, the average temperature or the bulk temperature would keep evolving along the flow direction. Similarly, something like that could also happen with respect to the solute transfer. So what we need to do is have a scaled profile for us to compare. So the scaled profile for velocity would just be Vx by V infinity, which is basically the velocity of the fluid divided by the maximum velocity that is there in the domain. On the other hand, for the temperature profile, it is scaled as follows: T minus Ts by T infinity minus Ts. And in the case of solute, it's the same way. We have scaled C minus Cs by C infinity minus Cs. So what we want to project is that under some flow regimes these three profiles would look same, which means after scaling their shapes would actually be similar, which means that the slope of this profile which is scaled would be same at the wall. So we are actually limiting the analysis to what is happening at the wall. So what we do is that slope at the wall is being given here. So this point where we are evaluating the slope at y tends to 0 is at the wall, and we are taking the slope here by taking the differentiation with respect to y. So the slope of the velocity profile scaled and evaluated at the wall, we are suggesting that it may be equal to a similar slope of the scaled temperature profile at the interface, and also to the scaled solute profile at the interface. Now if that is the case, then we can actually see how we can manipulate these three terms in a way that they relate to some quantities which we are familiar with. So for that analysis we will consider a hypothetical fluid. Why we say hypothetical is because we want to have the Prandtl number and the Schmidt number as 1. Naturally both these quantities, Prandtl number and Schmidt number, are properties, which means that this analysis is applicable only for such a fluid which happens to have these two numbers at 1. And Prandtl number is equal to 1 implies that nu by alpha is 1. So let us look at the definition of Prandtl number. It is nothing but ratio of momentum diffusivity to thermal diffusivity. So nu is basically kinematic viscosity defined as dynamic viscosity mu by rho, which is the density of the fluid. and the denominator is thermal diffusivity alpha is equal to K by rho Cp, and metals, liquid metals, are known to be low Prandtl number fluids. Now Schmidt number is defined as the ratio of momentum diffusivity to solute diffusivity, and so when we say that both Prandtl number and Schmidt number are same, what we mean is that these ratios mu Cp by K as well as mu by rho d are 1, which naturally means that the properties are now being defined. And by manipulating the terms across, we can actually see that this is equal to the expression that we have written here. So what we are trying to do by going from here to here is that we want to separate out the properties that are meant for the fluid, for the heat, and for the solute transfer, so that we can use them for our comparative analysis in a moment. When we say that mu is equal to K by Cp is equal to rho d, what we do is that we take mu and use it as a multiplicative factor for the slope of the scaled velocity profile at interface, and we take the K by Cp as a multiplicative factor for the slope of the scaled temperature profile at the interface, and we take rho d as a multiplicative factor for the slope of the scaled composition profile at the interface, which means that we basically simply take it here, okay, and that we do with a reason, because we see that mu into the slope of the velocity has a meaning that we already know from our unit on fluid flow. Okay, so when we multiply, we get this kind of an analysis. Okay, so we just simply multiply each of those terms with these respective slopes and equate them. So what we do is that when we look at these which are colored in a different manner, they remind us of quantities that we are familiar with. The first quantity would be reminding us of the shear stress at the wall. The second quantity will remind us of the heat flux at the wall, and the third one will remind us of the mass flux at the wall. So accordingly we write the quantities as tau by V infinity is equal to Q by Cp into delta T is equal to rho J by delta C. Now we make a further analysis, and we divide every of these three quantities with rho V infinity, and we obtain like this. We also divide with half and multiply with half for the first term alone, because tau by half rho V infinity square, going by our friction factor definition, would actually come out to be skin friction factor. So we'll want to have that half there, so we have multiplied and divided the first term alone with half. The second and third terms are not modified like that. All the three terms have been divided with rho V infinity. So now we can see that there is something that is familiar here, and also something that is familiar here. So we will look at them in a moment. So when we put these quantities together, we realize that the first term we have the skin friction coefficient that is sticking out, and in the second term we have got the heat transfer coefficient that is coming up, and this heat transfer coefficient, when we plug in, then h by rho V infinity Cp will actually come out to be the Stanton number, which is defined at this juncture, and the last coefficient we have here, that is actually the mass transfer coefficient. Okay, so we have put all these quantities together. So what happens is that Reynolds analogy states that the first term is giving us skin friction coefficient divided by 2, second term gives us the Stanton number, third term gives us the mass transfer coefficient divided by V infinity. So this is a very powerful analogy because it draws something that is similar across all the three transport phenomena. However, this analysis has used at certain point a hypothetical fluid which has Prandtl number and Schmidt number to be 1, which means that it is very restricted in its application. So this is where the papers by Chilton and Colburn come of great use, because they have actually used a multiplicative factor for the second and the third terms, which is basically the Prandtl number and Schmidt number raised to the power of 2/3, and then come up with a analysis which connects all the three transport phenomena. And very surprisingly, these three factors, which are referred to as J factors, happen to be valid for a wide range of the properties. So not only for Prandtl number and Schmidt number to be 1, they are actually valid for Prandtl number from 0.6 to 100 and Schmidt number from 0.6 to 2500. That's a very large range over which this analysis is valid. This actually implies that there are a lot of applications can now be possible. What are those? The applications are that we can use the J factor known from one phenomenon to determine unknown quantity in another phenomenon. By that, what we mean is as follows. We have already seen in an earlier lesson that the mass flux is a very accurate quantity that can be estimated during experimentation, because equipment with 1 microgram accuracy in weight loss are quite easy to have in the laboratory practice, which means that experiments that are done with respect to the mass transfer are very accurate. So such experiments, if they give us the data, can we use them also for heat transfer or for momentum transfer? That's exactly where this J factor analysis will be of use. Sometimes one of the three phenomena may not be amenable for experimentation. Nevertheless, we are able to make some conclusions on the quantities for those because of this similarity analysis that is made available to us at this point. There is another aspect also, that is there is a scaling of these quantities across the three transport phenomena in a wide range of properties, which also conveys that there is some universality of the subject across fluid flow, heat transfer and solute transfer. The subject has been dealt with in many textbooks on heat transfer, fluid flow and mass transfer in the mechanical engineering domain, and the discussion that I have presented here is taken from the book by Wiley, Wicks, Wilson and Rohrer, and this is a book that has a very general treatment of all the three transport phenomena in a nice manner with a lot of examples. I would recommend the students of this subject to refer to this book for further discussion. So here we see the beauty of all the three transport phenomena coming together.